I'll hand the exams back at the end of class, as usual. We're going to start chapter 4, which is it's basically applications of the derivative. We'll see all but one here towards the end. I recognize that these are sort of out of order with 4.2, but really the only type of like physical applications we have here is in 4.5. The other are like math applications.
So in the future, could you like post in each role what order we're going to be doing sections on, because it's a little bit annoying when I print off a certain number of sections and I find out that we're not doing half of them.
Yeah. So go by the schedule that's on the syllabus. The syllabus, last page of the syllabus has our schedule. And that's on D2L already, so you can just print that last page if you need to. So yeah, most of them are mathematical applications except for 4.5, which we'll save for last. Really 4.1, 4.3, and 4.4 kind of all tie together. And we're just trying to get a better picture of what a function looks like, or what its graph looks like in 4.1, 4.3, and 4.4. So we have various things, maximums and minimums, local maximums, local minimums, intervals of increasing and decreasing, that kind of stuff we'll look at more in detail with derivatives. And then 4.4 itself is just graphing functions using methods from algebra, pre-calc, and 4.1 and 4.3. 4.6, we're going to look at how to approximate functions linearly. So, like a trig function or a polynomial function can be approximated by a linear function. We'll look at that in 4.5. 4.2 is a really brief section about the mean value theorem. There's not a whole lot we do with that, but it does show up in other theorems. A few important ones in Calc 2. If you go on to Calc 2, you'll see the mean value theorem show up as like a justification of the proof. So it is a theorem that we're going to talk about. 4.7, we're back to looking at limits through more of a lens of like derivatives as opposed to computing limits. And in 4.7 is really dealing with limits that take the form 0 over 0 or infinity over infinity. Again, these things aren't 1, they're not 0, they can have any value. In the sense of a limit, it just means the numerators and denominators are approaching 0. It doesn't mean your function's 0. So we'll look at methods to evaluate those types of limits in 4.7. And then in 4.9, we look at the reverse or the inverse operation of taking a derivative, which 4.9 leads us into chapter 5. And chapter 5 is, the primary thing in chapter 5 is antiderivatives and what it connects to for us. So we end Calc 1 with antiderivatives, and you start Calc 2 with antiderivatives. So, I'll post this in our class notes, so you can reference that if you need to. So 4.1's about maxima and minima. Sometimes together when we say, instead of saying maxima and minima, they'll say extrema. So the highs and lows should be fairly intuitive if we looked at a graph. What's the high points, what's the low points. We're actually going to look at two different types of extreme values. One of them is an absolute, sometimes called a global maximum or a minimum, and the other one is a local or relative maximum and minimum. Okay. So there is a difference, this is why they have different names, but if you think about like an absolute max and absolute min, it's sort of like what's the tallest point on Earth, versus a local max would be like what's the tallest point in Colorado or the United States or the Northern Hemisphere. So there is a differentiation between those two things. We're going to look at some conditions for absolute maximums and minimums, and then look at the relative max and mins or the local max and mins. Because in order to find absolute max and absolute mins, you have to be able to find local maximums and minimums too. So we'll talk about absolute maximum and then relative, and then put it together. At the end, we'll look at identifying absolute maximums and minimums. So an absolute max and min are a global extrema. Hopefully it's really straightforward. It's just the highest point that the function takes and the lowest point the function takes. So that's kind of stipulated here. If the function value at c, some x value, is larger than f of x for all other x's, then we have an absolute max. If the function evaluated at c is smaller than every x, or the y value rather is smaller than every other x value, f of x value, then we've got an absolute minimum. Okay, and then here they say the absolute extreme value is either the absolute maximum or the absolute minimum. So what we're going to look at first is what are the conditions that are, what conditions must be present so that we can guarantee both an absolute maximum and an absolute minimum. Okay. So we'll just look at that with a specific example, nothing like really formal. We'll consider the function x squared on various domains. And again, we're after what conditions would guarantee us both an absolute maximum and an absolute minimum. So if we looked at, for instance, x squared on its domain, negative infinity to infinity, we would see here at its vertex that we do have an absolute minimum here. So I'll abbreviate that, absolute minimum. But there is no absolute maximum, right, because the function will just continue to grow. So there is no absolute max. Okay, so on its domain, it doesn't really work, and we'll see why. But then we can refine that, maybe look at x squared on the open interval from 0 to 2, including 2. We see here that there is an absolute maximum. But there is no absolute minimum here, because the function's not defined. Okay, so both of those intervals are actually open. Even though we're including the 2, we're not including the 0, so it looks like it's halfway open, halfway closed, but it's actually considered an open interval.
On the second one, the reason there's no absolute min is that because since it's not defined at 0,
Exactly.
you can get infinitely close to it without...
Right, yeah.
Okay.
So the reason there is no absolute minimum here is because we can't find the absolute smallest value the function takes on, right? We can get infinitely close to the x value of 0, but as we do so, there's always a smaller and smaller y value. And it gets worse if we look at the interval on 0 to 2, not including either endpoints. Here, in fact, there is no absolute extreme. So no absolute max or min on that one.
Thank you.
So the notion of the function is important, and we'll look at that. But right now we're just focusing on the interval. All of these were open intervals, and those open intervals didn't guarantee us both an absolute max and an absolute min. So what happens if we looked at x squared on a closed interval where we're actually including the endpoints? So then we see that we do have both an absolute max and an absolute min. So on this, we close the interval. So at least initially, we would be led to believe, all right, well, if I have some function, as long as I define it on a closed interval, meaning I'm including the endpoints, I can always define an absolute maximum and an absolute minimum, but it's not quite true. It's like half the story. So we've seen so far that we have to have a closed interval, but it's not the only condition that has to be present on the function. So if we look at this function, I don't know, this didn't come out very well. This is A and this is an x value of B. This function is defined on a closed interval because we're including both of those endpoints. Right, the function's defined at A and it's defined at B. But what do we notice about the function here on the left? Yeah, it's not continuous. It has an absolute minimum here at A and the same value here at B, but it doesn't have an absolute maximum. Similar situation, this function f of x on the right is defined on the closed interval AB, but it's not continuous on that interval. So we do have this absolute minimum, but no absolute maximum. And again, these are just a couple of situations. They could, there's infinitely many situations we could represent, but this is just to give us a sense.
Why isn't the absolute maximum the other point, the one that's right below it?
The one that's included here,
Yeah.
why isn't that the absolute maximum?
Because there's just a little bit of other piece of the graph that's above it.
Yeah, because we have all of these points. This point's larger than that one, this point's larger than that one, so is this one, so is this one, and so forth. Does that make sense? Does anyone have any other questions about that? Yeah.
So, like, if it's continuous and on a closed interval, then you definitely have it?
Yeah, so that's what we're going to conclude. Without proof, we're just going to say that in order for a function to have both an absolute max and an absolute min, the function must be defined on a closed interval, and the function must be continuous on that particular interval. And so that's actually proven or stated formally in the theorem on the next page, Theorem 4.1, the extreme value theorem. It says a function's continuous on a closed interval has an absolute maximum value and an absolute minimum value. Remember, when you describe these things, there's kind of two ways to describe it. If they're asking for the extreme value, at a location, then we give them the x value. But if they want to know what the maximum value or the minimum value is, then that's the y value. Typically, it's the y value you're after. Like it just, I don't know, maybe a time and temperature situation. You're going to ask what's the maximum temperature or the minimum temperature. You're not going to ask what was the maximum time or the minimum time. So the value is the y value. It occurs at the x value. Okay, so let's look at these two figures and state the absolute maximum and absolute minimum for these two. So the absolute maximum for the figure on the left is what?
A.
Is at x equal to a, and the value is f of a, whatever that y value is. Okay. What's the absolute minimum?
X is at X equals B.
At x equals
Oh, wait, no.
c. Absolute minimum. Whose value is f of c. So it's, an easier problem, I would say, to look at a graph and determine where these things happen. What we want to do is move away from looking at graphs to determine how we find these things. Okay. So the figure on the right, absolute max.
Absolute max, X equals C.
Absolute max at x equals to c. Does everybody agree with that? It's the overall highest point on that function. Whose value? So the maximum value we would say is f of c. Absolute minimum? No absolute minimum on this one. And again, we see that we can't guarantee both for that figure on the right because we don't have the function defined on a closed interval, right? It's defined on the open interval from a to b, and it's not a continuous function. So it violates both conditions of that previous theorem. Does anyone have any questions on that? Okay, then we'll define local minimum and local maximum. Discuss some details involved with these particular types of maximums and minimums, and then we'll come back to the absolute maximum, because these are a part of finding absolute maximums and minimums. So a local max or a local min says that we have this interval for which f is defined. That just means that, think of it as like a domain. So C is an interior point of that interval. So what does that mean to you if I said it's an interior point of that interval?
It's in between the two endpoints, like the X value is in between them.
It's in between the endpoints, right? It's not included. The endpoints are not included in that interval is what it's saying. So C, let's see what that means. It's really saying that C is inside or C is not an endpoint. And then it says if f of c is larger than or equal to f of x for all x. That was our definition for the absolute, but then this comes in and says for all x in some open interval around c. Then f of c is a local maximum. Similar situation if f of c is less than or equal to f of x for all the x values in an open interval around that, then it's a local minimum. And it is ambiguous. It doesn't say, it just says for some open interval, right? Like, it doesn't specify at all, is it an open interval that's, that size? Is it an open interval that's this size? What exactly does that mean? And it's not clearly defined. So we'll actually look at calculus methods to tell us exactly where those things are, and we don't have to worry about how big that open interval is, because we'll be able to find all of them. So that's for a local max or a local min. In order to be, what the definition is saying is, in order to be classified as a local maximum or a local minimum, that x value c is not an endpoint. So another way we can decipher that is to say that if you're going to classify something as a local maximum or a local minimum, then it cannot be an endpoint. Okay. Does anyone have any questions on the definition? Okay, so we'll look at the following example. It says identify all maxima and minima, and really what that means is we want to identify all absolute and local. Oops. All right, so let's just, it doesn't matter where we start. Let's just start with the absolute maximum. What's the absolute maximum of f of x?
Q and N, yeah.
At q. So here and here. Do y'all agree? It's the absolute maximum. So we'll just say at x equal q and x equal to s. How about the absolute minimum? At p. Do y'all agree with that? Absolute minimum at x equals to p. Okay. How about the local max?
S count for that. Q and S.
The same? You mean p? If you, is that what you meant, Allison?
For the max.
For the local max at q and s. Do y'all agree? Is that a local max here and here?
Yes. Yeah.
So yeah, those are definitely the highest points around that curve, right? So we're just thinking of an open interval around this, which really corresponds to this open interval, right?
Yeah.
Okay. Is that it? Are there any other local maximums? Are those the only two? At q and s.
The local maximum cannot be in it.
Right. Yeah, the local maximum couldn't be this point right here, even though this is the highest point. In that region, it's an end point, so we wouldn't call it a local maximum. Okay. Finally, local min. P. What do y'all think? Is that a local minimum at x equal p?
Yes.
Okay. And x equal p and x equal r? You agree with that? Do what? Yeah. So we certainly find an interval around x equal r as well. So that'll give us some visual sense of how the two can relate.
Maybe jumping ahead on this, but it's like kind of sometimes when you're locating the local max and local min, is it kind of like locating where the derivative equals 0?
Yeah, exactly. That's always it. So the question is when you're locating the local maximum and local minimum, are those things always occur? Well, I don't want to misrepresent your question, but does the local maximum and local minimum happen where our first derivative is 0? And in general, that's true. That's how we find where they are anyways. So also notice here though that we had an absolute max at Q and S, but that also was a local max at Q and S. So the local maximums and minimums could also be an absolute maximum and minimum. And that's why we have to take the detour and talk a little bit more in detail about local max and local mins and how to find them. Because if we're going to be given a particular function and it says find the absolute maximum and minimum of this function, then we've got to know how to locate locals as well, because sometimes they are absolutes. Okay. Any other questions on this example? So then just to add a little more to what we said about the first derivative being 0, here in Theorem 4.2, for the local extreme, remember Theorem 4.1 was the absolute or the global. I don't think they actually had a label on that. Theorem 4.1 was the extreme value theorem. Here is more specific because we're talking about the local maximums or minimums. Excuse me, in Theorem 4.2. And what it says is if f has a local maximum or a minimum, that means if we know this, so that's f of x. If f of x has a local maximum, then our conclusion is that the derivative at that location has to be 0. In other words, the slope of the tangent line is horizontal at that point. But it's important to note that this statement, this theorem, is not an if and only if statement. It's only meant to be read in the direction that it's presented. Meaning that if we have, or if we know that the first derivative is 0, that does not always guarantee that we have a local maximum or local minimum. Okay, so the converse of this theorem isn't true. The converse is that if, excuse me, f prime of c is equal to 0, then the function has a local extreme value. So this statement here is not true. We should say that if the derivative is 0 and exists, but the main idea is just because you have a location where your derivative is 0 doesn't mean you have a local max or a local min there. And so to support our converse is not true, the function x cubed has a first derivative that's 0 when x is 0, but there is no maximum or a minimum value there. So if you can just think of quickly the graph of x cubed. You know, look something like that. The derivative of x cubed is 3x squared, and we know that 3x squared is 0 when x is 0. However, there is no local minimum or local maximum there. Is everyone clear on how we interpret that? The derivative being 0 doesn't guarantee a maximum or a minimum. However, if we know there's a maximum or a minimum, we know that the derivative has to be 0. Okay, any questions on that? All right. So the thing we're going to look at to determine where the derivative is 0 is called a critical point. And a critical point, again, is interior to some interval. Typically, it's the domain of the function. Sometimes they give you like a restricted domain. It says, hey, look at x squared on the interval from -10 to 10. But the critical point has to be on the inside of the domain of a function. And those things, the critical point is where the first derivative is 0 or the first derivative doesn't exist. So we have to look for both places. Where is the first derivative 0 and where does the first derivative not exist? So these two figures here show that second part. Both of these are examples of functions who have a local maximum at a place where the derivative doesn't exist.
Can you scroll up just a
Yeah.
little bit?
Yeah. Yeah, sorry, I'm not fully aware of who all is printing these out, so if you need time to copy something, just let me know. But yeah, those two graphs illustrate, just one or two instances where you could have a local extreme, but the derivative fails to exist.
They're known as critical points.
They're known as critical points, yeah. So basically what the previous theorem 4.2, theorem 4.2, we can sort of recast that and say that if f of x has a local extreme value, a or n, whatever, then they occur at the critical points. Because critical points are just where your derivative is 0 or where the derivative does not exist.
So the local extrema are critical points, but critical points might not be extrema.
Right. So the local extrema, meaning local min or local maximum, will correspond to a critical point, but not all critical points correspond to local extrema. Again, think about the graph of x cubed. So as it says below, critical points are only candidates for your local maximums or your local minimums. So also a local max or min could also be the absolute max or min. So that's so like x squared from -2 to 2, the absolute minimum is also the local minimum. And we saw that with the first graphic example when we identified the absolute and the local as well. So I know that's a lot of information. Does anyone have any questions or need clarity on any of that? All right. So here's the procedure for locating the absolute max or min. We've got a continuous function on a closed interval, so we can guarantee both an absolute max and an absolute min. And then it says locate the critical points in the specified interval. Critical points, again, first derivative 0 or undefined. These points are candidates for the absolute max and absolute min. And just like we saw, the absolute max and min could also correspond to a local max and min. So the critical points are candidates for absolute max and min and local max and min. And it says evaluate the critical points and the endpoints of that function. So we're going to evaluate f of c, which were our critical points, and we're going to evaluate f at the endpoints given to us in that closed interval. Then to identify the absolute max, you just take the largest y value, and the absolute minimum, you look at the smallest y value. So you never have to look at a graph. All you have to do is find these particular x values where the absolute max and min can occur, and then you just plug those into the function to see which one's the largest and which one's the smallest. All right, since the first step to locate an absolute max and absolute min is to find the critical points, we're gonna pause with this absolute stuff and look at how we locate critical points, and then we'll come back to an example or two of utilizing this procedure. So we'll note that, we'll just say that in section 4.3, which is the next section we'll look at, we're going to look at 4.2 towards the end of chapter 4. So in 4.3, we will discuss how to locate our local extrema, our local maximums and minimums. But the first step in doing so is to find the critical points. And I'll just start abbreviating critical points. So in order to find both absolute extreme and local extremes, you have to be able to find the critical points. And we'll look at some examples of how to do that, and then build upon that the critical point notion in 4.3. So let's look at a few examples. Find or state the critical points. So I'm going to go back to the definition first, and just so we can remind ourselves, the critical point has to be interior, an interior point of the domain of your function. Okay? So we'll start off with f of x equals to 3x squared minus 4x plus 2. And just from algebra or pre-calc, we know quadratics will always have a minimum or a maximum value at their vertex. So this is just a light introduction. But other functions like exponentials or other algebraic functions, trig functions, it's not as straightforward to find where those maximums and minimums are. Okay, the critical points are, there's two things we're looking for. Where does the first derivative equal to 0? What x values does the first derivative equal to 0? And is the derivative undefined? For some x values. So then that naturally involves us looking at the first derivative. So the first derivative is 6x minus 4. Let me put this in the middle. And then we'll ask, okay, is this derivative 6x minus 4 undefined? Is that ever undefined? No, if it's a linear function, it's always defined. So is f of x undefined for some values of x? No. F prime is always defined. And then where does the first derivative equal 0? So this is where you have to start being a little bit more thoughtful about how you're writing derivatives, because you are eventually going to take your derivative, set it equal to 0, and determine where your derivative is undefined. And the simpler your derivative is, the easier these things are to answer. Like if you have this really complex derivative that could be simplified further, you're going to want to do that here. So we have our first derivative is 0 at 2/3. Our first derivative is never undefined. So our critical point for that quadratic is just at x equals to 2/3. And remember, critical points are only candidates for maximums and minimums, right? It doesn't guarantee us a maximum or a minimum when x is 2/3. Since it's quadratic, we could be probably 100% certain that it does correspond to the minimum value of that quadratic. But just as a general statement, right, for any given function, the critical point is only a candidate for maximums and minimums.
But it can, though, a critical point can equal a maximum or minimum value?
It can, yeah, right. And so again, we're not going to actually address that, whether that critical point is a maximum or a local maximum or a local minimum, until the next section. But I'll go ahead and graph these ones just so we can see for the upcoming section. So there's our x equals to 2/3. We do see in this instant that our critical point does actually correspond to a local minimum, but we won't know for sure until the next section. And this is sort of directly in line with those some of those position, velocity, and acceleration problems that you had in 3.6, where it says, you know, what's the highest point reached by the stone? It was quadratic. We set the velocity function equal to 0 because the velocity was the first derivative, right? So we're able to find those points, but now we want to sort of extend out to other types of functions that aren't just quadratic. So any questions on that example? Honestly, that's nothing we haven't seen outside of 3.6. So then we'll look at a few more involved examples. So let's look at the function x divided by x squared plus 1. We'll look at function's derivative using the quotient rule. I'll just write the derivative here. Minus x squared plus 1 all over x squared plus 1 squared. All right, so critical points, we find the first derivative. Then we look for where the first derivative is 0 and where the first derivative is undefined. So where's the first derivative not defined? At 1, what do y'all think? Is first derivative defined at 1 or not defined at 1?
It is defined at 1.
Should be defined over.
There's nowhere where it's going to
It's defined everywhere, right? Because when does x squared plus 1 equal 0?
be. Never.
Never at imaginary numbers, but no real number can make x squared plus 1 0. So I guess we could say something to the effect that f of x, or sorry, f prime of x rather, is always defined. You know, and another way to say that is that the domain of the derivative is all real numbers, right? It doesn't have any places we're omitting. Okay, where does our first derivative equal 0? Okay. At 1
And -1.
and -1. When does a fraction, our derivative is this fraction, when does a fraction 0? Only when its numerator is 0. So the first derivative is 0 when the negative x squared plus 1 is equal to 0. And so that's when x squared equals 1. At plus and minus 1. So the derivative is always defined. We didn't come up with any critical points there, but there's two places where the derivative is 0. Are these actually critical points, positive and -1?
Yes.
Yeah, how do you know? Critical points have to be where? In the
In the domain.
domain of the original function. So are we certain that plus and minus 1 are in the domain of this function?
If it's always defined.
Yeah. So you've always got to take that into consideration. You should always ask yourself, are these things that I'm about to label as critical points, are they actually in the domain of the function that's given to me? Right. Denominator's never 0, domain is all real numbers. Okay, then we can be certain that x equals plus and minus 1, both of those are critical points because they're in the domain of the function. So say here, since So that's our final conclusion there. So do those two critical points correspond to local maximum or local minimum? There's no way for us to know. We just know that if there is going to be a local maximum or a local minimum, then those are our choices, those are our candidates. there's the graph of f of x. And we can visually verify that our candidates at 1 and -1 do actually correspond to a local minimum and a local maximum. But again, I wouldn't worry about that until we actually talk about how we find the local maximums and local minimums. We're just sort of keeping that for future reference. All right, any questions on that, identifying critical points? I'll start. Okay, function number 3, find the critical points for the function 4 cosine squared on the interval from 0 to pi. So this one here, they do, or the example does give you a restricted domain. So that in effect is the domain you're dealing with here. Even though we know the domain for cosine squared is all real numbers, they're giving us a restricted domain. So that's the one we're operating with. So take a minute or two and compute the first derivative for 4 cosine squared.
Oh, no, you're absolutely right.
It's just only online communications.
Then you just hold it to you.
We can figure out where it equals 0, so it equals 0 at 0. And it equals at
You allowed to just hold it to you. Product roll. I'm sorry. One calculating the derivative of 4 cosine squared. That's a constant type of function, so you can just pull the 4 out and it's set the term. Then you can just change.
So what did y'all get? Somebody at this table want to volunteer what you got? First derivative?
8 cosine x times negative sine x.
So 8 cosine x times negative sine x.
Yep.
Okay, do y'all agree? Everybody get that? Okay. Okay, so then we've got the derivative. We want to know where does the derivative, to find the critical points, where does the derivative equal 0?
The other function with respect to the intent.
And where is the derivative undefined?
That's like u squared where u is cosine.
Now keep in mind, we're answering these questions, where is the first derivative 0 on the domain that's given to us on 0 to pi? And is f prime ever undefined on 0 to pi? So is negative 8 cosine sine ever undefined on 0 to pi? No. That function, the first derivative's function's domain is all real numbers, so it's certainly defined on a smaller set, right? So there is, we'll just say no, f prime is not undefined. So then when does negative 8 cosine x sine x equal 0? Yeah, let's see. How did you get it?
Where does cosine times sine equal 0?
Okay.
Like, on the unit symbol?
Yeah, right. So you've got 3 things that are multiplying to give you 0. The negative 8, the cosine, and the sine, right? So since those 3 things are multiplying, giving us 0, we can say that that's 0 when each one of those is 0. So when does cosine x equal 0, and when does sine x equal 0? So cosine x is 0. Cosine x is 0 when x is pi over 2, negative pi over 2, 3 pi over 2. You know, you can write all of these down, but you really need to think about the interval at which the function was defined on. The function was only defined on 0 to pi, so it's just pi over 2, right? We wouldn't consider all of those other ones as critical points because, you know, all of these other ones are not in the domain. From 0 to pi. So they can't be critical points. Same thing for sine. When does sine x equal 0? When x equals to 0 and pi. Anything outside of those two are outside of the domain. So x equals 0 and pi, do y'all agree? You shouldn't agree
Is it not interior?
because they're not interior points, right? These 2 points at 0 and pi are not interior to the domain. So these 2 points here, 0 and pi, are not critical points. Another way to think about that is we said critical points cannot be endpoints. Therefore, they are not critical points. So what are our critical points? Just pi over 2. Okay. So maybe something happens there on the function, maybe something doesn't happen there on the function. If we have a minimum or a maximum, a local minimum or local maximum, that's the only candidate that we have for that. Does anybody have any questions on this example? Yeah.
Do we include endpoints in global?
Yeah, the global or the absolute maximum or minimums, you do include the endpoints. So evaluate f at the critical points and at the endpoints for the absolute extreme. Okay, so there's 4 cosine squared from 0 to pi, and we came up with the pi over 2 value. So in this case, it does happen to correspond to a local extreme. But sadly, as we'll see in 4.3, that's just finding the critical point is like half the problem. To locate where these local extremes are, finding the critical point is half of it. Does anyone have any questions so far? All right. We'll take a break and look at a few more examples, and then we'll look at absolute maxims and minimums.
I'm at a 7. Something like that.
Okay, let's look at one more example, and then we'll go back to the absolute extreme. So we're finding the critical points for 1 over x minus the ln of x. And in most instances, unless it's a polynomial where it's like really obvious, hey, the domain is all real numbers, I would recommend that if you're identifying critical points, that the first thing you should actually identify is the domain of the original function given to you. So let's identify the domain of this function f of x. What would the domain of f be?
Negative infinity to 0. And then 0 to infinity.
Okay, so we with the 1 over x, for sure we have to exclude 0, right? But what about the natural log? Can we put negative numbers in the natural log? No, so the natural log says we can't use those negative numbers. So I guess originally we would start out from negative infinity to 0, 0 to infinity, but then the natural log comes in and says you can't include the negative numbers, right? So what's the domain? 0, not including 0 to infinity, right? So that's the domain of this function. If we come up with critical points, they have to be in that interval. So what is the derivative of f? Say that again, sorry. -1 minus 1 over x. Is that what you said, Allison? Yeah, what do y'all think? Right, so you gotta think of quotient rule on the 1 over x, or if we looked at it as x to the -1, it would be -1 to the x to the -2. Oh, too bad. So close. Or -1 minus x all over x squared. Just common denominator, add it together. Okay, first derivative, where is the first derivative? 0. And honestly, now that it's a fraction, it's much easier to tell where it's equal to 0. You would have had to done that eventually. I guess it's up to you as to when you want to simplify the derivative or rewrite it into a form that's more conducive to solving this equation here. And where is the derivative undefined? So usually those are the easier ones to answer. Where is our first derivative not defined? At x equal to 0, would we consider this a critical point? Yep, it's outside of the domain of the original function, right? Not included in the domain. So that is not a critical point. When does the first derivative equal 0? When x equals -1, yeah. So again, fraction 0 only when the numerator is 0. Is that a critical point? No.
No, it's a negative number, it's not a negative.
Again, outside of the domain of the function. It's not, let's just say it's not in the domain again. Okay, so that's it. We have no critical points. So there's the graph of our function. We don't see any local maximums or local minimums there. Okay. Do y'all have any questions on critical points? All right, then we'll go back to locating absolute extreme. So instructions are to find the absolute, extrema, just look at a polynomial to get a sense. X to the fourth minus 2x cubed on the interval from -2 to 2. So the procedure was to locate the critical points and then evaluate the function f at the critical points and at the endpoints -2 and +2, and then look for the highest y value and the lowest y value. So step one, we're going to locate the critical points. So we look at the derivative, where the derivative is 0 or undefined. Because remember, critical points could correspond to local maximums and minimums, and we saw two examples where the local were the absolute. Okay. So when does the first derivative equal 0? And when is it undefined? Or is f prime undefined? On the interval from -2 to +2, our polynomial function derivative is always defined. So it's not ever undefined, and our derivative is 0. When something happens. So we'll factor out a 2 and an x squared. So that way we've got two things multiplying, giving us 0. So it's 0 when 2x squared is 0, or when 2x minus 3 is 0. So x equals 0 or x equals to 3/2. Zero and 3/2 are certainly in the interval from -2 to 2. So these are our critical points. That's an arrow. Okay, so the procedure, find critical points, then evaluate your function at the critical points and the endpoints. So that's step 2, evaluate the given function f of x at the critical points and endpoints. So we're going to evaluate f at our endpoints and at our critical points. Let's see what those, we actually need the value for all of these because we've got to look at the highest or the largest and the smallest of these. So just some of the processes that we look at in the next section have us plugging things into the derivative. So you just need to make sure, like among those processes, when do I plug into the function and when do I plug into the derivative, as we'll see. But we're plugging these into the original function, x to the 4th minus 2x cubed. Okay, so f of negative 2, you should get that to come out to be 32. F of 2 is 0. F of 0 is 0. And f of 3/2 is negative 27 over 16. And all we do to determine the absolute max is the largest of these values. So our absolute max is 32. And we could say that it occurs at x equal to negative 2 if we wanted to, but the absolute maximum value is 32. And the absolute minimum is the negative 27 over 16 at x equal to 3/2. Y values. All right, so that's the process to find absolute maximums and minimums. Does anyone have any questions on that? So there's the maximum value, 32, and the minimum value here at negative 27 over 16. If I don't capture it. it won't let me click on that. Oh, you can see. All right. If there aren't any questions, we'll end that section. Start on 4.3. So then 4.3 is entitled "What Derivatives Tell Us." And so what they're going to tell us in 4.3, there's two things the derivative is going to tell us. And keep in mind, we're using the derivative to answer questions about some function that's given to us. So we're going to look at intervals of increasing and decreasing. And when we do that, it also will tell us where the local maximums and minimums are. And then we'll also use derivatives to tell us the intervals of concavity. And what we're going to look at is inflection points. So in part, what we get here in this section is how do we know or how can we guarantee that a critical point we've come up with is actually corresponding to a local minimum or a local maximum. So the way we test that is here in Theorem 4.7, and these two figures accompany what the theorem is saying. It says that if f is continuous on an interval and differentiable, what does differentiable mean again? You can define the derivative. So if the function is continuous and we can define or compute the derivative at all interior points, it says if f prime is larger than 0, in other words, if f prime is positive, or if the slopes of the tangent line are positive, so this one is for this one. If the slopes of the tangent line are positive in an interval, then that has to mean the original function is increasing. Similar thing, if the first derivative is negative, the slopes of the tangent line are all negative, then the function itself, f of x, is decreasing. So we can use the fact of what are the slopes doing to tell whether or not the function is increasing or decreasing. Does that make sense? Hopefully, at least visually, we can solidify that without describing this theorem in detail. So what it defaults to then is answering these two inequality questions. How do we solve an inequality? Do y'all remember how to do that? Because you're going to have to do that now.
Don't you set it equal to greater than 0 if you're doing increasing and less than 0?
Yeah. So let's say this function here. Let's say this is our derivative, and we have to answer the question: when is this thing larger than 0? And when is this thing smaller than 0?
You just solve it as an equals. You just got to compensate for the changes in the greater than or less than sign, depending on the quantitative method that you use.
Right. Yeah. So we're trying to figure out where it's positive and negative. So the first thing you actually do is figure out where it's neutral. Where does the function equal 0? And then outside of where it's equal to 0, it has to be positive or negative. So all we do there is just put a value into this to see, does it spit out a positive number or a negative number, and that'll tell us whether it's positive or negative. So do y'all remember doing that? Finding a 0 or something, and then picking a test point here and a test point here, and then saying, oh, hey, it's positive, and then it's negative over here. So that's how we're going to say that this function's larger than 0, and this function's less than 0 on those particular intervals. So state the intervals of increasing and decreasing for 2x cubed plus 3x squared plus 1. So intervals of increasing and decreasing have to be answered in terms of the derivative. Where is the derivative larger than 0? So when the derivative is larger than 0, f of x is increasing. Where the derivative is smaller than 0, then f of x is decreasing. Or I should say if f of x. So then again, we have to find the first derivative, and then to answer the inequality, we have to figure out where does the first derivative equal 0. So we can choose the appropriate test points. So we're going to look at where f prime, which is 6x squared plus 6x. Where is that larger than 0 or less than 0, but we have to first figure out where the derivative is equal to 0. So this again, it's not that we're finding the critical point. In a way, we're not considering where the derivative is undefined to answer the question about where it's positive and negative. We're only looking at where it's 0 so we can answer these two inequality questions. Okay, so we'll factor out greatest common factor. And see that our first derivative is 0 when x is 0 and negative 1. So that's how we're going to space up or space out our interval that we're testing with those two values we get. So here's f prime on its domain. We have here at negative 1 and here at 0. We know the function is 0 here. F prime is 0. So we have to pick our test values that are from negative infinity to negative 1. We're going to pick a test value here from negative 1 to 0, another test value, and sorry, I should do this instead, and a test value from 0 to infinity. It doesn't matter which ones we choose. We can choose any 3 numbers in those particular intervals broken up by our zeros. So on the left, what do we want to choose?
-2.
Okay, so we'll pick negative 2 in between negative 1 and 0, negative 1/2, and after 0, 1. So we're, again, just keep this in the back of your head. We're testing where the first derivative is positive and negative. These numbers, these test values, need to go into the derivative function, not the original function. So I would recommend when you're doing this stuff, label this thing here as f prime. That way you know that these numbers have to go into f prime. So we're going to evaluate f prime. It doesn't matter if you use the expanded version or the factored version of your derivative. All we're after is, we're not even after the value itself. We're just after the fact, is that value positive or is it negative? Okay. So evaluate f prime for the 3 test points we chose. So we're going to evaluate f prime at -2, at -1/2, and 1. Okay, so we have 6 times -2 times -2 plus 1. So we have -12 times -1, which is -2 times -12 times -1 gives us a positive. And then so what that means here is that if we looked at our first derivative from the interval -∞ all the way to -1, the first derivative is positive. So we're just going to put that positive there. Any questions on what we're doing or why we're doing it? We're trying to answer this question. Where's the first derivative larger and smaller than 0? Yeah. So f prime of -1/2. And I think the quicker way to evaluate the signs here is just to look at the first derivative. You've got 2 factors. What does each factor become? Because if we know first factor is positive and second factor is positive, then we know the outcome is positive, and so forth. So 6 times -1/2, that factor is negative, plus 1, that factor is positive. So you have a negative times a positive, which gives you a negative. So our first derivative is negative on the interval from -1 to 0. And when x is 1 into the first derivative gives us a positive result.
We can't just assume that it's going to be an alternating pattern of positive and negative, can we?
Right, so you never want to assume that it alternates. Particularly here, what we're dealing with is a polynomial. So like a polynomial could do this, right? But a polynomial could also do this. So at these zeros, it really depends on the behavior. Is the polynomial crossing through the zeros, or is it actually just bouncing off? So that if you remember from algebra, that's determined by the multiplicity of the zeros. How many times that factor occurs determines whether a polynomial will cross through or bounce off of its 0. But no, we can't assume that it'll alternate. You actually need to go through the test for each test value. So then really all we're after is this sign chart here for f prime. So just look at it visually to see that our whatever numerical result actually fits in with our first derivative, 6x squared plus 6x.
Plus 6x. You got it.
Plus 6x. All right, there we go. I'm just going to copy this and paste it next to the sign chart. I mean, this was a quadratic, so there's not any weird behavior with a quadratic, right? It opens up, crosses through, that's it. But if we were to superimpose this sign chart onto our first derivative, maybe it gives you a visual sense of what we actually determined, right? Where is it above the x-axis? Here and here, which are this one here, and where is it below? It's right here. So with more complicated first derivatives, it's entirely inefficient to try to graph the first derivative to answer where it's above and below the x-axis. Is everybody all right with that? Maybe it's been a while since you've seen or solved inequalities, but that's how you do it. You never really look at a graph unless it's an easy function like a quadratic. It's probably more efficient just to graph it. But any other function, it's way more efficient to look at the chart. And I'm just going to rewrite what we had here, just so we can look at the direct connection. So our f prime situation was this. And so what that tells us about the function itself, again, if the first derivative is positive, then on that interval your function is increasing. If the first derivative is negative, the function is decreasing. So this sign chart that we computed actually just gives us this piece of information here. Does anyone have any questions? Yeah.
We basically just write it as like f of x is increasing on the interval from here to here,
Yes.
and here to here. Okay.
Yeah, and please don't just write this on the exam. If I ask for the intervals of increasing, I know it's implied here, but write it out and say f of x. I'm gonna keep doing that. F of x is increasing on the interval from negative infinity to negative 1 and from 0 to infinity. And so forth. F of x is decreasing on the interval negative 1 to 0. So write that out instead. And then there's the graph of the function f of x. And we can so we can visually verify that what we did is correct. Questions on that?
As a reminder, when do you use, when is it valid or applicable to use the u between your intervals?
I guess it's just a matter of the
If you were to
particular.
write it with a u instead of a comma, would that technically be in?
No, I don't think so.
Okay.
I know my math lab doesn't like that.
Yeah.
It'll
Yeah.
say, write your interval.
Separate with a
interval
comma.
notation, separate with a comma.
Yeah.
But if you're like not paying attention to write it with a U, it'll count it wrong.
Yeah.
I made that mistake before.
Yep.
Isn't that a different notation? There's like a specific.
Yeah, I
Yeah,
can't remember.
it's-
I wasn't sure if that's.
It's and I've seen other authors use the union, so I don't think it's generally agreed upon. It is from set theory, And it's basically just read as or. So it's increasing on this interval or this interval. Our author, the author of our particular textbook uses commas to separate. About the only time I've seen the union is when they're describing the domain of the range. If you get through all of this stuff and you put a union in there by accident, then just email me instead of redoing the whole problem. All right. Okay, so why don't y'all try the function x times e to the negative x. Find the intervals of increasing and decreasing.
We're going to give you an example.
So I just want to make sure I'm not getting off track here. So we have first right? So 1 times we take times the second one, plus the second.
You can't put something to a power.
So that
Oh, no.
Forgot to find the derivative first.
Yeah, so there's a literature.
Here, and I'm like, I get confused when it's like
Technically,
powers to it.
so you take
Put it underneath. Yeah, that's like how I can remember. That was scary.
I mean,
Wait.
if it works, you get the answer for it. Go for it. That's all I got to say.
So I would just like write it out as what I as I see it, because then that way I know exactly what to take the derivative of and what to leave.
they're right, it is time.
So when you say first times the derivative of the second,
Just write it out just
plus 6 times the second times the derivative of the first, and then that way I know like all I have to do is take the derivative here, but in this instance I have to take it along.
And in what cases, because like this, I can see clearly we're doing product rule, symbols record, but in what cases do I know, like let's say this was negative 1x, negative 2x, whatever it is, how do I know this by using the chain?
If it's anything other than x1,
Okay.
so like derivative.
So it's negative ETS plus e to the negative.
I get the same thing.
Negative 3x.
Yeah.
I said it because we're not taking the derivative. The opposite. Okay. Taking the derivative. I mean, you still have the same answers. All of this is multiplied by negative 1.
So this would be negative.
Yes. Remember, we take the derivative and you do a power, the power stays.
Okay, so for this one, we won't plug in.
Yeah,
we get here.
Yeah, because if you raise anything to 0,
And this one's just itself, right? You just take the derivative of times 1.
I've seen it practice like following through the problems because I think like I've made most of my mistakes.
It'd be way easier for me to
Like I've
do
made
the fraction and then just make it
For sure.
I'll try.
All right.
no, I'm the opposite way. I like having negatives out there because I'm like, okay,
There's a lot happening here.
The other reason why is because when you set it equal to 0, you can just set the top equal to 0.
I bought a set of expos.
He did the X and that versus 0, right?
So there's no critical points?
There is no critical points. Set of function equals to 0. And the question is, does the strength x ever not?
Well, doesn't it have to fulfill both in order to be critical?
Basically, any power.
Oh no, the drawing I was gonna draw.
Yeah, it
was gonna be really interesting.
Have you seen the show The Society?
But it's 0 to 1.
Maybe that's
no.
Those are Okay, so this one, you never, this is, there's no critical value.
Yeah, and there's nothing over there.
But then it doesn't equal 0.
This is where
They talk about getting it, but I don't know if maybe.
You had a different
This one's the barn here with it.
And then you do the negative x.
No, because if you use that x,
Because you said this is the derivative. So here, crosses a 0
Is it?
that means on the future side.
And have that under
Can you start writing on that? I think I like it better to keep it.
It helps me visualize what's actually going on.
Am I getting it? Here's one.
we do have
That was my quick one. Because I haven't felt very inspired.
So you would place.
I got 1 and 0. Negative 1. Negative 1.
Yeah. Which is 0, so that's equal to 1. So that's all.
Different way than you guys. Not like, alright,
And then it'd be increasing from infinity to 1, decreasing from 1.
With weird thinking, you have like mixed algebraic exponentials, logarithms, exponentials, and powers of x. You just want to take out the greatest common factor. That way you've got two things multiplying.
Are these ever included?
I'm not sure. I've always been confused about.
Yeah, right. So exponentials
I
are
don't think it ever does.
So just so we try to solve for 1. So you play it. So that's
Okay, I just figured out how 1 works. So make it I mean, that's so you say x.
I know, that's a lot easier.
So we have
So what we do
negative
is
plus zeros to the
And that's the highest
So
point?
these two are basically make each other zero. So if we set this to negative 1,
Okay.
Yeah, so you chose.
Not that I
so
really
then
figured it out.
this in turn
why I
becomes
thought.
negative. So
Let's say we draw
this times negative 1 is just negative plus.
We have those points.
Yeah.
We just make up these points.
It does not matter what the powers are.
X equals 1.
Oh, yeah.
Okay, so now we want. And then we see.
So that's why one of these are critical value.
Otherwise, stuff like this. No, so it's immune.
I can't wait to get back to a point in my education where I can just cut open together. That was really
So much fun.
So it's just X.
Yeah, but I think what it's in this instance, I
And I can stop doing math.
Yeah.
Or when I am doing math, I'm doing statistics.
Yeah.
Well, we know that they're doing
I was looking at this. He said what my potential is, like on the metro navigation app.
Yeah.
What the salaries are.
Nice.
And I really love that there's nothing that just the
It might just not be the minute.
Unfortunately, you need a master's.
You're gonna see what you get. That's like the one time that you can actually get people there. Is this correct? Is one our critical value? Like, okay, cool. Okay. Super good.
Average salary for years.
It's increasing.
Oh, do the same thing, okay.
Yeah.
Right, because we have for both possibilities. I mean, our
So far, so good.
Like I'm doing it, but
Yeah, mine is.
I don't know why I was
All the numbers is always, those are always negative.
I love all these pages and stuff, but I hope that didn't come out all
I mean, I still get everything.
Something helped me like change my like that. No, I mean, this is like.
Oh, yeah, I know.
Well, I thought it helped until I got my results out.
So it's always.
I figured that out.
So I got 0.
But the good news is it's 1 point higher than our last exam, but I still want to But I'm just frustrated because it's not outside of the I just didn't
So just a word of advice here. So this derivative equation can be solved in another way, but I would recommend when you have like mixed expressions like algebraic, like x to the power, square roots, and exponentials, or like powers of x and logarithms, and those things are kind of mixed. In general, when you're solving where the derivative is 0, the main method to solve there is to pull out the greatest common factor. So that's going to work pretty much every time. You don't have to actually pull out the greatest common factor here to solve, but in general, that's the method you're going to use, because then you'll end up with a couple of things multiplied together to get 0. So we'll do that here. And set each factor equal to 0. So when x is 1, we get as the first derivative is 0. And then there are some questions about e to the negative x. There's a couple of ways to think about it, I guess. If you remember the graph of e to the negative x, looks kind of like that. It's never 0. The other way is just to solve it analytically, to involve the inverse, right? So we'll say, let's take the natural log of both sides. Can we take the natural log of 0?
No.
No, so you end up with negative x is equal to something that you can't define. You know, so what that means is that the original equation, there is no solution to the original equation because you end up with something that's not meaningful here. But in general, any exponential is never 0. So just, you've got to remember that, I think, is the easiest way to remember it. The only way these exponentials are 0, of course, is if you shift them, right? Like if I took e to the negative x and I shifted it, then it has a 0 there. But you would see that come out in a more algebraic procedure like we've done here. I don't want to erase that. Right, so let me just say, like, what if we had e to the negative x minus 2, and we want to know when that equals to 0. So that will equal 0 somewhere. Just because we have an exponential doesn't mean it's 0. We're just saying that if it's only an exponential by itself equaling 0, it will never equal 0, right? So you see this process unfold like, okay, well, when does e to the negative x equal to 2? That's when negative x equals to the natural log of 2, when x equals negative ln 2. So you solve that way with exponentials. So you only have one critical, you only have 1 0 of your first derivative that you have to test. So what is the domain of the original function f of x? Yeah. So the x equals 1 is something that we're going to test here on the first derivative's domain from negative infinity to infinity. All right. I saw most of y'all had gotten that far, so that's good for now. So then we'll choose 2 test values here and here. And we're evaluating the first derivative at those values. So I don't know, 0 and 2. But our first derivative was this, and I always use the factored version because if you know the sign of all of the factors, then you know the sign of the first derivative there. So e to the x, I'll just write it here as well. E to the x is always, or sorry, e to the negative x rather, that's always positive. So this, your derivative has a factor that's always positive here times whatever this sign is here. And when we plug in 0, you just have negative 0 plus 1. So that's going to be positive when x is 0, which means that you've got a positive times a positive. And when x is 2 in the first derivative, you're going to get that factor again, always positive, negative, or sorry, 2 in here makes this factor a negative, and negative times a positive is a negative. So that's what you're dealing with, the first derivative. If you want to, you know, I think most people were plugging that into a calculator, which is fine, but I think it's just as easy to look at the factors. Could save some time. So what does that mean about our function? F of x is increasing on this interval, and f of x is decreasing on this interval. Right? Does anyone have any questions on that? All right. So where the first derivative is positive, the original function is increasing. Make sure you go up to that 0 of your first derivative here at 1. This is we're always partitioning that that number line, if you will, involving the first derivative by the zeros you obtained for the first derivative equaling 0. And then and decreasing from 1 to infinity. Box that in. Okay. Anybody have any questions on that? So a couple of things to mention. I didn't really take points off. If the instruction said simplify and you didn't, I didn't take points off for some of those. But just moving ahead, if the instructions say to do something, make sure you do that. The derivative of the log base 2 of 9 showed up as like a true-false question. Log base 2 of 9. That's a constant function, right? So the derivative should be 0. And a lot of people, on example 4, where you had to find the second derivative of the log of x, a lot of people were writing y equals to the natural log of x and just finding the derivative of that. You just created a completely different problem.
Because it's 10 to the
Yeah,
power of
this is
y
log
equals
base
x.
10, right? They're not the same function. So unfortunately, if you did that, you lost all points because you just made up a problem.
I probably did that.
A lot of you are also writing the derivatives of logarithms as like 2ln. You should be writing that as natural log of 2 or whatever. Like ln by itself is just like writing a square root by itself. It has no meaning. So you have to have something attached to the natural log.
What is the square root?
The function where it's e to the sine x squared, that is not the same thing as e to the 2 sine x. That is only a property of logarithms, not of exponentials.
But it is 2 natural log of e to the power of sine x, right?
Is what?
Is essentially 2 times the natural log of e to the power of sine x. That's correct though, right?
It's a different function though, totally different. Like if we introduce ln here, then we have to introduce ln to the original.
Or I guess more so, yeah, I guess more so specifically, I would only use that if I was doing the,
logarithmic.
yeah.
Yeah,
log, but,
yeah.
Yeah.
If you took that, that's equivalent to the natural log of 1.
Okay.
And logarithmic differentiation, if you stopped here, I took off points because it's really not much simpler. So some people just stop with that. That's a product and a power rule. So you're taking the derivative of this, which is not really that much easier than what you started with. So you need to simplify this more. An object strikes the ground when its position is 0, not when the velocity is 0. So just look over the test key that I posted, and if you have any questions on what you missed, please ask.
Yeah.